afternoon, everyone. Thank you for having us. My name is Ayomide, Aisida, and together with my teammates, Kosisochukwu, Obiora, Leona, and Bishop Akalusi, we present to you DermaBridge, a trustworthy multimodal AI system for equitable skin lesion screening, explainable risk assessment, and smart clinical referral. This project was developed under the guidance of our graduate mentor, Leona and Adeika, and our faculty mentor, Dr. Saroj Pramanik. The main problem that we saw to address with our project was racial bias, as most dermatology models often suffer high misdiagnosis rates on darker skin tone due to severe data imbalance. So DermaBridge is an AI-powered screening framework and mobile app that combines dermatoscopic images as well as clinical metadata to deliver accurate and fair lesions classifications. It shows how AI can reach diagnostic fairness across all skin tones without sacrificing accuracy. The four objectives of our project was to curate a multimodal data, mitigate bias across our architectures, embed explainability, and build a prototype. Our primary research for this question is, can a skin lesion classifier be designed and selected to be able to perform equitably across the pediatric skin type 1 to 6? This question further broke down into two. 1, does the most accurate model also turn out to be the fairest model? 2, does fine-tuning of darker skin tone actually help to fix this fairness gap, or does it depend on the model architecture? To answer this, we built a unified benchmark from 6,000 data sets. We built 10,250 images with better dark skin representation. We also benchmarked 5 image architectures under one identical pipeline, and we evaluated this model using a 3-tier fairness framework. Our best model was chosen with its micro F1 score and its fairness band, after which we then fed the model directly into our DermaBridge AI mobile app prototype. So before developing DermaBridge, we first conducted research. We have carried studies have utilized AI for skin lesion classification. So through this, we discovered that early work with convolutional neural networks showed that deep learning models could automatically detect diagnostic patterns from dermoscopic images, even to the point of reaching dermatologist level performance. So another study expanded on this using the multimodal vision transformer by combining not just dermoscopic images, but also additional patient information through a mutual attention mechanism, which led to an accuracy of 92.4%. Another framework called MISC utilized a similar approach using the MobileNet V2 for image analysis and combined that with a random forest model for analyzing patient information. And this led to an accuracy of 95%. So through this, we covered the importance of combining not only visual data, but also patient information. And that is the approach that DermaBridge uses today.
So looking at that, DermaBridge has looking at that as the issue across studies. So most of these things overall accuracy on those data sets. This is your attention on fairness across the diverse data. DermaBridge compares 5 architectures under one single pipeline. Also, audit skin tone fairness, flexibility, and support neural explain. So looking at the pipeline, so the local pipeline, the local DermaBridge controls like the pipeline, which consists of different processes. So the first process in the pipeline was defining the problem. And then most of the issue that there was a first issue across the middle of the process, after defining the problem, we merged the data set into one data set, and then brought out 10,250 images from the data set. And then went on to the processing process and we stratified sampling process. Then we do dividing the data set into 17 process. And we feel like 15 for testing and 70 for tuning and 15 for validation. And then we moved on to train the 25 modules under one simple identical pipeline.
After training of these models, we evaluated them using a 3-tier fairness framework. During the first level, we evaluated them by their binary management report. The second level was their true quantitative grades between the light and the darker skin. And the third evaluation was the true positive rate under the DACA scheme alone. Then we went to a second phase of fine-tuning, where we trained this model using only DACA scheme data sets, and then validated this model on all the old data sets. After that, we chose our two models to ensemble with GradCam. After assembling this model, we directly integrated it into our app, DermaBridge AI. So this slide particularly sums up our data and model into one line. We had 6 data sets, 8 classes, and 5 modules. We unified 6 publicly dermatology data sets, the HAM 10,000, the BCM 20,000, the FASHIC 17K, PADUFES, MR Midas, and Stanford DDI into a benchmark of 10,250 images. At the right-hand side is our diagnosis distribution across classes. One of the things we noticed about our data set that it was imbalanced with basal cell carcinoma and melanoma taking up roughly about half of our data set, and vascular cell lesions sitting at just half a percentage. The orange bar represents the malignant or pre-malignant cases, while the green bar represents the benign cases. Because of this imbalance, fairness across classes and not just skin tone was important throughout our project. For our models, we benchmarked 5 image net retained backbone, which is the ResNet 50, EfficientNet B0, EfficientNet B2M, convolution net base, and swine transformer, which we selected as our specific backbone. For our preprocessing and training recipe, all images were resized into 224 by 224 RGB. We stratify our data set by diagnosis and skin type. Also, heavy augmentation and inverse frequency weights were done for the Fitzpatrick B to 6 in order to increase more data sets since we had less representation of the DACA scheme. And Adam W, cosine annealing, and label smoothing were used for our model optimization. So we trained our models, and with our data we split used the classic 10-15-15 split, which we stratified our split by diagnosis as well as pediatric before we augmented any of our data. And to prevent linkage, we had to cross-verify each image ID. And in our test set, we had 53 malignant dark skin cases compared to standard DDI 48, which is considered gold standard across the dermatology. For our technology, we use Python, PyTorch, and scikit-learn for our full pipeline, leading from data processing to model training. We also make sure to track core performance metrics using accuracy, precision, recall, macro F1, AUC, and completion metrics. And then we tracked and evaluated fairness using the purpose TPR, recall gaps, equalized odds, dark skin reliability, and reducing confidence intervals. This was really essential because it allowed us to track model evaluation, fairness evaluation across all different skin tones. We also incorporated some interpretability tools such as GradCam and SHAP, which enabled us to better understand how our model would be. This slide shows the results of our test accuracy and micro F1 score of all the 5 architectures that we benchmarked. 2 of our best performing architecture were the convolution next and the swine transformer, with the test accuracy at 76.7 for convolution next and 75.6 for swine. They surpassed the other 3 architectures with a difference with about 14 points. When choosing our best model, we didn't just consider their test accuracy. We had to think about if they were fair across each dark skin representation. That's why we use the recall gap. The recall gap compares the difference between the recall in the darker skin versus the recall in the light skin. And we compared the recall gap after fine-tuning, that's after we fine-tuned the model. Swine transformer, which was the second best performing model, had the best recall gap, which made it our best model since our criteria was test accuracy, micro F1 score, and recall gap. And swine transformer had the best performance altogether compared to the convolution net basics. Convolution net. So just to reiterate, when comparing our best models, we noticed an important trade-off between fairness and accuracy. So although our complex model had the highest accuracy of 76.7%, it also had the largest recall gap across dark skin tones. This means that its high aggregate performance hid disparities and failed to show how well it performed across diverse skin tones and populations. On the other hand, our slide transformer had a nearly identical accuracy of 75.6%, but it also made sure to balance its recall across all the skin tones, with reaching a near parity of 0.93 for both the light and medium skin tones and 0.94 for the darker skin tones after fine-tuning. So our results are basically showing that, like my again with Kosi said, high accuracy does not always equal fairness. The high overall accuracy can hide serious diagnostic failures as well as missed cancers on darker skin tones. Also, fine tuning, when it comes to dark skin, fine tuning is not a one size fits all situation. It relies on each base model architecture. And model choice must balance macro F1 as well as cross skin tone recall gaps. And to answer our research questions from before, accuracy and fairness diverged, and the most accurate model was not the fairest. While fine-tuning and proportion to fine-tuning effects depends on the base model, hence it is not consistent. Prioritizing fairness during selection yielded balanced performance across all skin tones. During our research, we unexpectedly found that fine-tuning widened the fairness gap for 3 out of 5 our architectures, and we confirmed that legacy data sets cause drops on darker skin tones and challenges reporting aggregate accuracy alone, which considers the disparities.
Slide shows of how the market works. First of all, that division in your portfolio, one for you actually can do it on one. You know your camera on the phone, photo scan, vision, you can manage the AI app. And then after scanning vision, how you will actually your skill goal, depending on how well that you are, but it's on you up now. And then it helps like improve the intelligence of the AI app. After that, after start to continue and compounding the result. Then the app will teach you the results of your usually you have to on type of answer. So they show that the answer is almost cells and then you directly to narrow the methodology for care and treatment.
So now on topic, we encountered with two challenges, one of which was data set quality. So initially, our data set contained missing values, inconsistent labeling, and different formatting. And this was an issue because it delayed model development because we had to spend additional time cleaning and preparing our data before model training. But to resolve this, we made sure to remove duplicates, handle missing values, encode labels, and merge all of our data sets using one consistent format. Another issue that we ran into was the limited representation of skin tones and also the annotation of the labels. So initially, our data sets contained fewer examples from certain skin tone groups, primarily the darker skin tone, and it also lacked complete skin tone labels. And this made it really hard for us to track and evaluate branding across all skin tone groups. But to resolve this, we incorporated the specific skin tone categories, which then allowed us to make product evaluation with qualified evaluation.
Tomorrow, even not happen, and we have limitation surrounding them. Before being based on communication, doing that is into the role like how we program image situation. The diagnose to passing and passing skill slightly still in there and people down this Also, based on generalization, many discuss people include diversity for different factors like other factors like population, battle, lighting, and based on the internal contact application. And looking at bias and fairness issues, our bias is way on not arise or unequal population and small samples. And this was accessed to between and
We conclude that architectural design and targeted fine-tuning directly determines whether a model can achieve equitable classification across all skin tones. Our framework proves that fairness-aware evaluation is the core design of medical AI and not in the end. For our future research directions, we want to test the fine-tune split on independent hospital datasets and diverse imaging hardware. We will also like to integrate a gradient-boosted meta-learning to lift our accuracy and equity. We will also like to use an IRB approved collection of underrepresented dark skin malignancy and integrate them into our DermaBridge AI app for usability tests. Now, on behalf of my research group, I would like to express our gratitude towards everyone for contributing towards the success of this project. I'd like to start by saying a special thank you to our faculty mentor, Dr. Pramanik, and our graduate mentor, Ms. Blessing, for their mentorship and guidance from start to finish. I would also like to thank my fellow members, Leona, Bishop, and Ayomide for their diligence and collaboration throughout this project. And then I'd like to say a special thank you to CEAMLS for this opportunity to participate in the SAIRI program. And I would also like to thank all program coordinators as well as the guest speakers and instructors for their help and guidance. We truly couldn't have done this without all of you, so thank you once again.